Hello everyone, welcome back to another episode of Solving LeetCode question. Today's question is gray code. An n-bit gray code sequence is a sequence of 2 to the power of n integers, where every integer is in the inclusive range from 0 to 2 to the power of n minus 1. The first integer is 0. An integer appears no more than once in the sequence, and in addition, the binary representation of every pair of adjacent integers differs by exactly 1 bit, and the binary representation of the first and last integers differs by exactly 1 bit as well. The question is, given an integer n, return any valid n-bit gray code sequence. Below, we have 2 examples. In the first example, n equals 2. So we know that the sequence will contain numbers from 0 to 3. Let's look at the output here. The output sequence is 0, 1, 3, 2. Here we can see that 0 and 1 differ by 1 bit, which is the rightmost bit. And 1 and 3 differ by the left bit. 3 and 2 differ by the rightmost bit. And finally, 2 and 0 differ by the leftmost bit. Therefore, this is a valid gray code sequence. In the second example, n equals 1. And the output is simply 0 and 1 because they're 1 bit apart from each other. How do we solve this question? Pause here if you like to think independently for a moment. Let's look at more examples to see if we can find a pattern. When n equals to 3, the solution is 0, 1, 3, 2, 6, 7, 5, 4. We can do a quick check and see that each pair of elements differ by exactly 1 bit, and the first and last element also differ by 1 bit. Looking at the 3 examples, we can see that as n increases, the sequences are built on top of each other. In other words, to get to the solution for n equals to 3, we can focus on n equals to 2 and see how we can make use of it to derive the solution for n equals to 3. When n increases, we have an added bit to the left. So to complete the sequence, the missing numbers all have the leftmost bit set to 1. If we transform the original sequence by setting the leftmost bit, we'll arrive at a new list with elements 4, 5, 7, 6. Interestingly, if we look at the solution for n equals to 3, the added list is 6, 7, 5, 4, which is exactly the reverse of the transform list. Why does this work? This is because the solution for n minus 1 is a valid gray code sequence. So with the added bit set to 1, we still satisfy the condition that adjacent elements in the transform sequence are still 1 bit apart. Now, why do we need to reverse the list? This is because the first number in the second list, let's call it y, is transformed from the first number in the first list, let's call that x. So they're 1 bit apart. So to satisfy the gray code condition that the first and last elements are 1 bit apart, y needs to be put at the end of the new sequence. Similarly, the last number in the second list, let's call it n, is transformed from the last number in the first list, let's call that m. So they're also 1 bit apart. And therefore, m and n need to be next to each other to satisfy the gray code condition. Finally, to set the added bit to 1, this is equivalent of adding 2 to the power of n minus 1 to every element from the original list. In summary, we'll use recursion to solve the problem. The base case is when n equals to 1, and the answer is 0 and 1. At each recursion step, we'll first add 2 to the power of n minus 1 to gray code of n minus 1. Then we'll reverse the new list and append the reverse list to gray code of n minus 1 to derive gray code of n. The Python code is as follows. The final time complexity is 2 to the power of n, and space complexity is also 2 to the power of n because we're computing a list with 2 to the power of n numbers in 1D space and time. That's it for today. Let me know if you have any questions, and see you next time.